In the last video, we had discussed the structural rules of the grammar of mathematical logic. Now suppose we are given a sentence following all those rules. We want to change that sentence slightly. Perhaps changing the order of two parts or converting a for all to a there exists or something like that. How would the meaning of the sentence change as a result of this change? That's what we want to explore in this video. The first rule is about the order in which the quantifiers appear in a sentence. If there are some identical quantifiers in consecutive positions, then their order does not matter. The meaning of the sentence would not be affected by the order. Consider, for example, two consecutive for alls. Just reverse their order, the meaning remains the same. A similar guarantee works for consecutive there exists as well. So, people often prefer to club consecutive identical quantifiers. This may be done only when the associated conditions are all the same. For instance, here both the conditions are belongs to R. So, we may club them like this. But if two consecutive quantifiers are different, one is a for all while the other is a there exists, then changing their order would change the meaning of the sentence. Let's understand this with the help of an example. Consider this. Some blue disks connected to some purple disks. Let B denote the set of all blue disks and P denote the set of all purple ones. Then is this sentence correct for this configuration that you see here? For all x in B, there exists y in P such that x links with y. Yes, it is correct. Because whatever blue disk we take, you can always find a purple disk linked with it. Like this goes with this goes with this goes with this. Note that this y in there exists may depend on the x in for all. For instance, this purple disk serves the purpose of this blue, whereas this purple disk serves the purpose of this blue. The same purple disk did not work for both of them. It depends on which blue you are talking about. Be careful here. I am not saying that each blue disk must have its own exclusive purple disk. Here, for instance, I have one purple disk which serves the purpose of both these blue disks. I am merely asserting that the purple disks may be distinct for distinct blues. This assurance comes from the fact that the for all comes before the there exists. Had the order been the opposite, then the sentence would not remain correct for the configuration shown. Because here we are claiming that there is a purple disk, exists y in P, that is connected with all the blue disks for all x in blue. As you can easily see for yourself, no such purple disk exists here. But had the configuration been like this, then even this sentence would have been correct because here is a purple disk that is connected with all the blue disks. Is the original sentence still true in this new configuration? Of course, because there we only cared about finding some purple disk for each blue disk. We did not care if the purples were distinct or not. So what have we learned so far? Suppose that there is a sentence with an exists immediately after a for all somewhere in it. There could be other quantifiers before or after this. Now, if we bring that exists in front of the for all, then we shall get a stronger statement. That is, if the second statement holds in some context, then the first statement must also be true in that context. But if the first statement holds in some context, still the second statement may not hold. It may hold, it may not hold also. This scenario is often encountered in mathematics. The second statement is usually called the uniform version of the first. Like from continuity, we get the concept of uniform continuity. This means that in the definition of continuity, we have an exists immediately after a for all somewhere. The new definition obtained by swapping just these two quantifiers gives us the definition of uniform continuity. Another such example is to start with boundedness and arrive at uniform boundedness. There are many other such examples as well. We shall return to details of these in some later video. Suppose that we have a sentence, I love apples. What is its opposite? It is this. This sentence is the negation of this. Similarly, this is the negation of this. When you have a sentence and its negation, then in any given context, exactly one of them must be true, the other false. While writing down proofs, especially in a proof by contradiction, we need to find the negation of a given sentence. The main weapon for that is this symbol. It means not. First, write down the sentence you want to negate in the language of mathematical logic, and then pass the not symbol over it. This changes the for alls to exist and vice versa. Finally, the not will negate the very last part of the sentence directly, and this will give you the negation of the entire sentence. Confusing, right? Let me explain with an example. Consider this class of students. Here is the statement. All the students in this class are boys. In mathematical language, it is for all x in class, x is a boy. Is this correct for our class? No, because I can see at least one girl. Here, however, I can actually see two girls. But even the existence of at least one girl falsifies our statement. So the negation of our statement is this. There exists x in class such that x is a girl. We arrived at this negation by considering this picture. It is difficult to do for a more complicated sentence. But there is always a direct method for negating any sentence. Just put a not before the sentence. These two sentences mean the same thing. But it is difficult to appreciate the meaning of a sentence when there is a not starting at the very beginning. So we prefer to transform this statement to its equivalent but more intelligible form. For this purpose, we shall take the not gradually over the sentence from left to right. When it will pass over a for all, the for all will change into a there exists. Now, at the very end, we have this. X is a boy. When the not passes over it, it becomes just its opposite. That is precisely what we had got earlier also by considering pictures. Here, negation meant turning boy into girl. In most mathematical proofs, however, we do not deal with boys and girls. There, we work with these symbols, equality and inequalities. We need to remember who is whose opposite among these. For instance, this is the opposite of this is the opposite of this, and this is the opposite of this. The way we got an exists by negating a for all also indicates that the negation of an exists is a for all. Because out of these two sentences, you can think of this as the negation of this or this as the negation of this. So if I start with this and put a not in front of it, then this exists will turn it into a for all when the not passes over it, and finally when the not passes over this, the girl will turn back into boy. This technique will allow you to negate even rather complicated mathematical sentences. Take this sentence as an example. This looks scary, but don't worry. You do not need to know about bipartite, non-planar, quasi-conformal or dual in order to negate this sentence. Just enough to understand that here we are talking about something called a graph, and that there is a type of graph called bipartite, non-planar, and another type is called quasi-conformal. And one graph can be the dual of another graph. That's all that you need to know. Immediately we can write the statement as for all G in Bn there is H in Qc such that H is dual of G. So here, as you might have guessed, Bn stands for the set of all bipartite non-planar graphs. Similarly, Qc stands for the set of all quasi-conformal graphs. We are supposed to find its negation. Let's start by adding a not right at the beginning. It is not clear what this means, so we shall start moving the not forward. The first step. Here, this for all has turned into a there exists. In the second step, this there exists is going to turn into a for all as this moves over it. Now, it has come to the very final part, so we shall negate it directly in the third step. Now the meaning is quite clear. Let me read it in plain English. There exists a bipartite non-planar graph such that no quasi-conformal graph is its dual. Well, that is all for this video. The next video will take a closer look at and or.